Hello guys, how are you doing?
Good afternoon.
Hello.
Hi,
Good morning.
good afternoon.
Hello.
Hi, nice to see you guys. Okay, so first question will be, did you have a chance already to practice with long kappa? Does everything work smooth?
Yes, but we haven't been graded yet. But other than that, yes.
Yeah, sure. You will not be graded for this week.
But will we be able to see if our submissions were correct?
I think that you will at the end of the assignment, at the end of the week.
All right, thank you.
Sure. Okay, hello, everyone who has just joined to us. So maybe a short recall of what we considered last online discussion. So it was motion along a straight line. So we introduced the main concepts of parameters which are necessary for describing motion in space and time. Okay, there's one more question. No. So how it works? So there is a question: should the questions change every day? Should we do them every day? So you get set of problems, something about 10, 12 problems per week. They will not change. It could happen that this time, I believe questions like problems which are the assigned to your homework. But yeah, so you get 10 or 12 problems, or call it questions, but that's actually technically problems. So they will be the same for all week. So you can take your time and do it when it's convenient. You will get it every Monday, and the deadline is every Sunday, like Sunday evening. So you can decide when you solve these problems and try to submit the answers to long kappa. This time it could be some change because I had a discussion with other instructors, and they were initially for this past week, there were added some problems on standard deviations. And this topic is not covered properly in the textbook. So it could be that you had some changes in the list of problems which were assigned to you, but this will not happen again. So it will be just assign 10 problems or 12 problems, and then you will deal with them until the end of the week. Okay, so we introduced last time the main concepts for describing position as a function of time. That means instantaneous velocity and instantaneous acceleration. And consider probably the easiest example, which is motion along straight line with a constant acceleration. So we got some main kinematic equations, which we can write down to recall, and then we will add one which we haven't yet derived. Let me change the camera. So we got the following equations. Position as a function of time. It's defined by initial position plus initial velocity times time plus initial this constant acceleration times time squared divided by 2. So for velocity as a function of time, we got initial velocity plus acceleration times t. And now, just in order to save time for considering next topic, but if we express time from the second equation, it will be like v minus v naught divided by a, and substitute it in the first equation, we will get another useful equation which describes velocity as a function of position. So then we kind of eliminate time from the equation. And sometimes when problems don't deal with, they're not given time, but given all initial parameters, then also given final like position in given moment of time, then it can be very useful. So we get such equation: v squared is equal to v naught squared plus 2a times x minus x naught. So this we get by substituting time in the first equation by its expression, and just shuffling around the terms of equation in order to express it for velocity. So these are three most important kinematic equations which allow us to describe motion of a body along straight line with constant acceleration and predict its position at any moment of time. So now next topic which we need to work with is two-dimensional motion. So in this case, things become a bit more interesting. So now let us consider some system of coordinates with x and y. So in this case, both axes responsible for position along axis x and along axis y respectively. We have some, let's call it trajectory or path of moving body in this two-dimensional space. So position of body could be given with so-called position vector or radius vector, sometimes it's called. And if it moves, let's say from point A to point B, there will be different position vector which will define position of this point in a two-dimensional space. So how what kind of vector it will be? So here we have vector delta r, which is a change of position vector because of motion from point A to point B. So obviously, according to rules of adding vectors, we have vector, like resultant position vector will be r, vector r plus vector delta r. So this is the main concept of defining position in two-dimensional space, and it's also true for three-dimensional space, just that this vector, position vector, has more components. Now it has two components, and in three-dimensional it will have three components. But in order to describe motion, two-dimensional motion, we also need to introduce this main parameters, which we discussed previously, but define them a little bit differently because we had motion along a straight line. So now we deal with two-dimensional case, and we always will deal with vectors. So first is average velocity, which is also vector. It's equal to delta r, change of position vector, over delta t, some time interval. If we consider limit of delta t approaching to 0, we will automatically define the instantaneous velocity. So let's write this. Instantaneous velocity will be defined as limit delta t approaches 0, delta r over delta t. And this is equal to the derivative of delta r vector over delta t. Here, one comment should be made. It is possible to take derivatives of vectors because, like, from a mathematical point of view, it looks like some vector dr divided by some small scalar number. So the result of applying derivation, taking derivative from a vector results in another vector, which is velocity vector. So another parameter which we need to consider is also instantaneous acceleration, and that is related to the speed of changing the velocity. How fast velocity vector is changing over time. So instantaneous acceleration, again, it will be limit delta t approaches to 0, delta v vector over delta t. It is first derivative of velocity vector over time, or it is second derivative of position vector over time, dt squared, and your vector. So now the main question of kinematics of motion in 2 dimensions remains the same as it was for the motion in 1 dimension. We need to define position of our body, in our case, position vector, at any given moment of time. So this is the main question which we need to answer. And in order to show how we can address this question, let us consider again one standard case when we have motion in 2 dimensions with a constant acceleration. So let us go to another slide and consider this specific case. So obviously we deal with position vector, and that in 2-dimensional space can be split in 2 components. So it will be x times I vector, unit vector I, plus y times j unit vector. So now the velocity vector will be defined as derivative of the position vector. dr vector over dt. And obviously we can differentiate, we can take derivatives from the components of this vector. like separate and independent. So dx over dt times I vector plus dy over dt j vector. This is equal to Vx times I and plus Vy times j. So what do we see here? That our velocity vector, we can also split in two components and consider motion. So instead of considering motion in 2 dimensions directly, we can simplify our life. We can go and split it into two components. Then we will deal with two motions along straight lines, along the axis x and y. And then it will be with appropriate velocities along this axis, along these perpendicular directions, and can consider them independently from each other. So they don't interfere, don't have any feedback, and we can consider these two motions along straight lines, which synergetically result in the motion in 2 dimensions. We can consider them separately and apply rules for which we already derived, and the equations which we already derived for the motion in along a straight line in 1 dimension. So according to those rules, and we just refreshed in our memory our previously derived equations, assuming that acceleration is constant, we defined this at the beginning of this consideration, then we can also, so this is constant, we can also write that components of this acceleration along axis x and along axis y remain also constant. So ax is constant and ay is constant. So now we can define time dependence of these velocity values, like amplitudes along axis x and y as a function of time. So it will be Vx is equal to Vx naught, means initial velocity along this axis x, plus acceleration along axis x, which is constant, times time. The same we can write for y axis, velocity along y axis, ay times time. So now we have expressions for time dependence of the amplitude of Vx and Vy, and we can write in a different form, like more like in a general form, equation for velocity in 2 dimensions as a function of time. For this purpose, we will do the following. So velocity in 2 dimensions as a function of time is equal to this time-dependent component of velocity along axis x, Vx naught plus ax times t, this times I vector plus Vy naught plus ay times t times j unit vector. Now, if we rearrange, like open parentheses and rearrange, so we have velocity and acceleration components separately, we will get the following. It will be Vx naught times I vector plus Vy naught times j vector plus ax times I vector plus ay times j vector, and that times t. So we have here our total initial velocity vector will be v naught vector, like sum of two vectors, plus our total constant acceleration vector. It will be a vector times t. So eventually we get v as a function of time vector is equal to v naught vector plus a vector times t. And graphically, we can represent it as follows. So we can show here some system of coordinates. And if we have, for instance, our initial velocity vector, v naught vector, then we have this acceleration component, a vector times t, and resultant, maybe we can move it here, v naught vector. Resultant will be the sum of these two vectors, and that will be v vector at a given moment of time, so at the same time t. So now we define how it looks with velocity, resultant velocity vector in case of two-dimensional motion with constant acceleration. We also know how to deal with its components along different axes. And next step, we can apply next equation, which we derived for the position along straight line for the one-dimensional motion, which will be describing each of the two components of this two-dimensional motion. So we can write for x position as x naught, initial x position, plus v x naught times t, plus a x times t squared divided by 2. The same we can write in this case for position along axis y as a function of time. Y naught plus v y naught times time plus acceleration along axis y times t squared divided by 2. So finally, we can sum everything up and get the expression for the time-dependent position vector. So position vector as a function of time will be equal to the sum of position, like vector sum of positions along axis x and y. So it is x naught plus vx naught times t plus ax t squared over 2 times I unit vector. And that also plus component along axis y. Y naught plus vy naught times t plus ay t squared divided by 2. And this is multiplied by j vector.
Sorry, can I ask a question?
Sure.
Sorry if I probably missed this when you explained it. What does ax t squared over 2 represent again?
Oh, it's a component of displacement along straight line, which is responsible for constant acceleration.
So it's
if we don't, for instance, if we have constant velocity, zero acceleration, obviously this component will be equal to zero because ax would be equal to zero. So let's say if it accelerates, we have two-dimensional motion and it accelerates only along axis y, then we will have x is equal to x naught plus bx naught times t without this component. And all this acceleration will be responsible for accelerating along the axis y. However, we consider a more general case when we have accelerations in both directions.
So what it represents is how much displacement was done due to the acceleration, right?
Exactly. Yeah, that's what we actually derived last lecture. You can maybe take a closer look on that derivation process when we did second integration of time-dependent velocity, and we end up with this contribution from constant acceleration to total displacement.
Thank you.
You're welcome. So now we can again rearrange these components, group them by types. So initial position, initial velocity, and constant acceleration. So will be x naught times I plus y naught times j. Then we have components responsible for velocity, initial velocities along axis x and y. And finally, we have acceleration components. It's ax times I plus ay times j, and is times t squared over 2. So again, we get the final expression, which is r naught, initial position vector, plus v naught, initial velocity vector, times t, plus constant acceleration vector, times t squared divided by 2. So you see that by applying this approach of splitting two-dimensional motion into components, we can apply previously derived equations for displacement along straight lines, which are defined by this axis x and y. And then by adding vectors, we can come to the general equation, which describes in vector form position vector dependence on time. Also, let us show this total displacement in graphically. Partially would also address this last question which we discussed. So we have initial position vector r naught, then we have component of change of this position vector because of velocity, initial velocity, v naught vector times t, and one additional component because of change, like a component of changing the position vector because of acceleration. It will be a times a vector times t squared divided by 2. So the resultant position vector r at time t will be defined as the sum of these three components, contributions to the change, to the new position of the body in two-dimensional space over some time interval. Okay, so let's go further with this, and we can discuss one example, quite common and classical example of motion in two-dimensional space, which is called projectile motion, or motion of a body thrown at some angle to the horizon. So what do we have there? We need to consider that this motion of like projectile motion, let's assume that it starts from the ground, and this is our axis X here, Y. It starts here. It looks like some curved path, which starts at the ground, reaches its maximum height of the trajectory, h. Here we have initial velocity, v naught vector, at some angles theta naught to the horizon. And here it is called the horizontal range. Let's call it R. It's a distance from the throwing point to the landing point. So these are the most important information about this projectile motion. Obviously, there are two most interesting points here. It's actually point A and point B, which will define maximum height and horizontal range. In order to proceed with the development of some model which will describe this motion, we need to set two conditions. So first we deal with free fall acceleration. So we know that there is G free fall acceleration, and that it is directed downwards to the ground and doesn't change in the range of motion of this projectile. So means that the maximum height is, and this horizontal range is small in comparison to the radius of the planet Earth. So let's say we can write that h is much smaller than Earth's radius, and horizontal range also is much smaller than Earth's radius. So why it's important? Because later we will discuss this in more details when we study gravity, but the strength of gravitational field decreases with distance from the planet, from any object. And obviously this as a quantitative parameter of this strength of gravitational field, free fall acceleration, free falling acceleration g is also a function of height. But we can neglect with this because usually these projectiles don't go so high that it should be taken into account. Another factor which should be taken into account is we neglect with the resistance of air. So we assume that the speed is not too high and the shape of the body is kind of aerodynamically optimized, so that the resistance of air is considered to be negligible in comparison to other parameters. So in this case, we can analyze this motion in the scope of the model, which is valid for two-dimensional motion with constant acceleration. So in this case, we should split the initial velocity which projectile is given at the beginning of its motion into two components. We need component along axis x and component along axis y. So Vx naught, initial velocity along axis x, which will be here, Vx naught, and here we have Vy naught. So this will be equal to V naught times cosinus theta naught, and Vy naught will be equal to V naught times sinus theta naught. So we have two components, and we now need to understand how these components will change over time. So Vx as a function of time will be equal just to Vx naught, and this will be constant. Why? Because we discussed this already. We don't have any resistance from air, and our acceleration is aligned downwards, so means it's aligned only along axis y. So it doesn't have any projection on axis x. Its projection is equal to 0. So that's the case when we have acceleration only along axis y. And another component, which is what velocity along axis y as a function of time, will be equal to Vy naught plus ay times t. So we know that j, so this free falling acceleration g is aligned downwards, so it is aligned in opposite direction to the axis y. So we can write that a acceleration along axis y is equal to minus g, and that's why we write that Vy is equal to Vy naught minus g times t. So now we know time dependence of the components of the velocity vector along axis x and y, and we can proceed further with some analysis of this motion. So let's go to another slide. So first, let us consider what will be the highest point, this point A of the trajectory. Let's draw it again here. This is our trajectory. This is point A, and this is the highest point at some height h from the ground. We want to know what will be the highest point of this trajectory. So obviously, the highest point will be reached when the y-axis component of initial velocity of this body will be equal to 0. So it will reach the highest point, will kind of stop, and then will change its direction of motion along axis y. It was initially positive, and then it will be negative displacement along axis y. So we know that Vy at point A will be equal to 0. So again, equation for time dependence of Vy is Vy naught minus g times t. And this will be equal to 0 at point A. And this time will be, let's call it TA, which is time when the body will reach point A. So from this equation, we can express this TA. TA is equal to V naught times sinus theta naught divided by G. So we have time at which the highest point of the path will be reached. So now we can consider equation for the position of the body along axis y in order to determine the maximum height. So y position at time A, TA, so it's in the highest point, will be initial position of the body along axis y plus Vy naught times TA plus, or sorry, not plus, but minus, because we have negative orientation of acceleration, minus G times TA squared divided by 2. So now we substitute this expression of time TA in this equation here and here, and get the height, the maximum height of the trajectory. So H is equal, so we have, assuming that R y naught is equal to 0. Why? Because we start from the origin of the system of coordinates. So initial position of the body is defined by coordinates x equal to 0 and y equal to 0. So taking this into account, we express also this Vy naught, initial velocity of the body along axis y, which will be Vy naught equal to V naught times sinus theta naught. It will be V naught times sinus theta naught. Then times TA, and TA is this expression. So it will be V naught sinus theta naught divided by G. And minus G divided by 2 times V naught sinus theta naught divided by G. It's TA, but we have TA squared, so it will be all in the second power. So now, if we open parentheses here in the beginning, we will get V naught squared times sinus square theta naught divided by G minus 1/2 of V naught square times sinus square theta naught divided by G. So here we have G in second power, and here we have G in first power. That's why we get G in the first power in the denominator. So it just second term is half of the first term. So eventually we will get for the maximum height, it will be V naught square times sinus square theta naught divided by 2G. Okay, so with this we finished. Now the second question which we want to consider is what will be the horizontal range, this R. How far this body, this projectile will fly away from the initial point along axis X. So in order to address this, we need to consider, okay, if it takes TA time to reach maximum point, like highest point of the trajectory A, it takes the same time to fall from this highest point back to the ground. And means that TB, let's call it point B, TB will be equal to TA times 2. So it will take time twice longer. So taking this into account, that TB is equal to 2 times TA, we can determine the horizontal range. It will be equal to Vx naught, which is constant, it doesn't change over time, times TB. Quite simple. Now, instead of Vx naught, we write V naught times cosinus theta naught, and that we multiply by 2 multiply TA. So we use expression for TA, and that will be 2 multiply V naught sinus theta divided by G. So now if we group everything together, it will be 2 V naught squared times sinus theta naught times cosinus theta naught divided by G. And taking into account the trigonometric identity that sinus 2 theta is equal to 2 sinus theta multiply cosinus theta, we can write the final equation for the horizontal range of projectile motion, and that will be V naught squared times sinus 2 theta divided by G. So let us consider this final equation, a bit more detailed. So maximum horizontal range will be equal to V naught squared divided by G. And why? Because maximum value of sinus 2 theta is equal unity. And that will be when 2 theta is equal 90 degrees, or theta is equal to 45 degrees, like theta naught, initial angle at which this projectile is thrown. So that defines the condition for the maximum horizontal range. So we considered during this lecture, introduce the main parameters of the motion in two-dimensional space, and showed that it's convenient to split two-dimensional motions to 2 or 3, depends on number of axis motions along straight line, which coincide with the axis of our system of coordinate. And then we can do all these mathematical manipulations with these components and sum up and get the resultant position vector as a function of time. So we considered this on an example of projectile motion, It's one of the standard example of two-dimensional motion with constant acceleration, which in this particular case is aligned only along one axis of this two-dimensional system of coordinate because it pointed always downward. And based on these assumptions, we derive equations for their position along axis X and Y in this projectile motion with constant acceleration, and define the extreme points, means the maximum height of the projectile trajectory, and also the horizontal range. This is pretty much everything I wanted to tell you, and yeah, you're welcome. I also think that it is very important to see the derivation and step by step understand how they show up, not just read them in textbook, but try to understand and derive them, and also to have some short analysis of final equations in terms of results which they give to us. So to consider some extreme points of maximum and minimum values, define some ranges of possible results which this equation is giving us. Okay, yeah, guys, if you have any questions, you're welcome to ask me. And don't forget to practice with long kappa. That's important for your future grade. And thank you very much for attention. I wish you a good day and hope to see you on Friday.
Goodbye. Thank you.
Goodbye.
Thank
Thank you.
you.
Thank you. Goodbye.
Bye-bye. Thank you.
Bye. Thank you.
Bye.
Goodbye.
Have a good day.
See you.
Bye-bye.